Hello, today I'm presenting two topics and they are wave interference and standing waves. They aren't exactly related, but they do share similar aspects. So what is wave interference? Wave interference occurs when two waves are in the same place at the same time, and all the peaks will line up with the peaks and the troughs will line up with the troughs. They aren't difficult because it only involves addition and subtraction. There are two types, and they are constructive and destructive interferences, and I'll be talking about them in future slides. So constructive interference is when waves combine to make a larger wave. And it's simple because if the waves are going the same direction, just add them. Here's an example of constructive interference. You can see that A is here and B is here, and they converge to make A plus B. Then a moment later, B and A go on as if nothing happened. So destructive interference is the opposite of constructive interference. Destructive interference is when waves combine to make a smaller wave. So if they're going in the opposite direction, subtract. This is an example of destructive interference waves. A is going to the right and B is going to the left. A moment later, this is A plus B and they cancel each other out. Then after that, they go on as if nothing happened. Sound wave interference is another type of interference, and interference of sound waves can be demonstrated with two identical sound sources, demonstrated as two loudspeakers, right here and here. The full lines represent crests and the dotted lines represent troughs. So these are troughs and these are crests. Positions where the crest from one source crosses a crest from the other so as to give increased amplitude are regions of constructive interference, and they're labeled by C here. So these are crests meeting together. Conversely, positions where the crest of one wave combines with the trough of the other so as to give zero or a very small amplitude are regions of destructive interference, labeled D. So right here is destructive, this is destructive, and here's destructive. The loudness of the observed sound from the two loudspeakers is at a maximum along the C lines and a minimum along the D lines. So here is where you would hear the most sound, labeled constructive. D is where you would hear the least sound, and so on and so forth. So the next topic is standing waves, and standing waves are when identical waves travel in opposite directions, and the amplitude of the two waves produces a wave that does not travel. In order to have a standing wave, the string needs to be vibrating at a constant frequency. Each wave is reflected from the fixed end, and when the wave comes back at a hand, it will be reflected as if the end is fixed. And the crest and trough of the waves are always at the same positions. So unlike wave interference, standing waves has an equation we need to use in order to find frequency or the length. So using the wave speed equation, we can find wavelength, and wavelength is equal to velocity over frequency. Another equation we need to use is this one. Any number of waves can fit on a string that is L long. But remember, the wave travels across the string twice back and forth, so it's 2L instead of 1L. Now we are going to substitute lambda for velocity over frequency over here. So moving frequency to the other side, we can get it by itself and get the standing wave equation. Frequency equals NV over 2L. So this picture is just to show you all the possibilities of standing waves. For example, if there's one standing wave, then N equals 1. And over here, N equals 2 because there are two waves. So using the equation F equals NV over 2L, we can find either the frequency or length just by counting the number of waves here. So N equals 3 over here, so it would be 3V over 2L, and over here there are 4 waves, so it's 4V over 2L, which simplifies to 2V over 2L. So that is all I have for today. Thank you for watching.